Okay, the mass of a neutron is slightly higher than the mass of a proton, and in nuclear physics this can be important. So also in nuclear physics, instead of using kilograms as a unit, sometimes we use the atomic mass unit U, which is equal to 1.661 times the power minus 27 kilograms, which you can find in your data sheet. And this is basically 1/12 the mass of a carbon atom. And so the mass of a neutron is 1.00867 U, and the mass of a proton is 1.00728 U. Okay, in nuclear physics, there are a lot of calculations involving energy as well. So we need a convenient unit for that as well. Okay, so what I'm going to do is I'm going to use Einstein's equation equals m0 c squared, and I'm going to apply that to the atomic mass unit. So I'm going to do the atomic mass unit 1.661 times 10 to the minus 27 times the speed of light squared. Okay, and that gives me this number here. Okay, that's still not convenient to work with. So I'm going to turn that into it's a very small energy. So I'm going to turn that into electron volts. I'm going to divide that by 1.6 times 10 to the power minus 19, and that gives me 9.3 times 10 to the 8 electron volts. And now that's a bit big in terms of electron volts anyway. So I'm going to turn it into mega electron volts by dividing this by 10 to the 6. So I get a mega electron volts of roughly 931.5 mega electron volts. So 1 U corresponds to an energy of 931.5 mega electron volts, and you can find this in your data sheet. Okay, the nucleus of an atom is held together by the strong nuclear force, which attracts all the protons and neutrons together. In order to separate it, I need to do some work. Again, this is called the binding energy. So the binding energy of a nucleus is the work that must be done to separate a nucleus into its constituent neutrons and protons. Okay, we're going to try to find the binding energy of this carbon-12 nucleus. The nucleus itself has a mass of 11.99671 times the atomic mass unit. To figure out the mass of the separated nucleons, we just use the mass of the neutron and proton, and because there are 6 of each, we multiply them by 6 and we add them together. And you find that the mass of the separated nucleons is actually larger than the nucleus. Okay, why is there? What's the difference between these two? Well, it's the separated nucleons have extra energy that we've put in the binding energy in order to separate them. Okay, and this difference in the mass is called the mass defect. Okay, the mass defect is defined as the difference between the mass of separated nucleons and the mass of the nucleus. So in this case, it's 0.09899 U. This mass defect actually corresponds to a binding energy. So I can use 1 U to turn into kilograms, and then I can turn that into an energy. So if I multiply that by 1 U, I get the mass defect in kilograms, and then I can multiply that by c squared to turn it into joules, here like this. Okay, but it's easier to visualize what's going on by using mega electron volts instead. So I can use 1 U, which is equal to 931.5 mega electron volts, which we showed earlier on, and multiply by that. So the binding energy here is 92.09 mega electron volts. So that's how much energy would be required to separate the carbon nucleus into its constituent protons and neutrons. Okay, another useful number is called the binding energy per nucleon, which is just the binding energy of the nucleus, which is we calculated a minute ago, divided by the total number of nucleons in that nucleus. So in this case, we've got a binding energy of 92.09 mega electron volts, and there are 12 nucleons inside it. So we get a binding energy of 7.67 mega electron volts per nucleon. And this binding energy basically tells us how stable the nucleus is. The higher the binding energy, the more stable that nucleus is. Okay, in this example, I'm going to find the binding energy per nucleon of krypton 89. Okay, so the mass of the nucleus is being given in atomic mass units here. Okay, I want to find also the mass of the separated nucleons to get the mass defect. So I'm going to go to the data sheet and figure out the mass of those. Okay, and write those down. Okay, so we've got the mass of the nucleus here, and I'm going to deduct from that the mass of the protons, the separated protons. There are 36 protons. So it's 36 times the mass of each proton. I'm deducting that, and then I need to figure out the number of neutrons. 89 minus 36. So it's 53 neutrons. So 53 times the mass of the neutrons. I'm deducting those, and that means I get a mass difference, or a mass defect of 0.75009 U. Okay, now I need to turn that into an energy. I'm just going to use the fact that 1 U corresponds to 931.5 mega electron volts, and that gives me the binding energy. So that's how much energy would be required to separate this krypton 89 nucleus into its individual nucleons. But what we want is a binding energy per nucleon. So we're going to have to divide by 89. Okay, so we take that, divide by 89, and that gives us 7.85 mega electrons per nucleon.